Good morning, good afternoon, good evening, and thank you for joining us for this installment of the SPWLA The More You Know series. My name is Kim McLean, and I am the team lead for the Formation Evaluation and Drilling Technical Team at Emerson in North America. And today, what I'm going to do, I'm going to start off by sharing my screen and getting into slideshow mode. What we're going to talk to you about today is an integrated petrophysical interpretation approach to help us unlock and understand our unconventional reservoirs. The work that we're going to look at here was done for a client to help them make the best choice in terms of original oil in place with regards to which well path to use as they move forward with their drilling program. And I'll explain a little bit more as we get into the bulk of the talk here. So this is our roadmap for today. We're going to start off talking about the purpose of the study, which I alluded to when I introduced the topic. Then we're going to go into a workflow overview. How did we approach studying the well? How did we approach studying the data and analyzing the data? We'll take a closer look at the petrophysical and geomechanical analysis of our offset well, and then how we can take our understanding of the offset well and apply it to the proposed well paths. And through that, help us decide which of the well paths is going to be the best moving forward for their drilling program. I'm going to spend more of our time in a demonstration, actually going through the workflow within the software. And anybody who knows me knows I prefer to show instead of tell. So I actually don't have very many slides, 7 in total. So we're going to spend the bulk of our time within the Geolog well application, and then we'll come back with some conclusions and key takeaways before, obviously, the Q&A sessions that we have immediately after airing of this. So I want to thank Sitel for giving us the permission to actually show the data that I'm going to present today. The data was divested to them from the client that we worked with. And the idea behind the study was to integrate our petrophysical interpretation, geomechanical interpretation, as well as the electrofacies modeling that we've been doing on the well to help us identify sweet spots within our zone of interest. In this instance, it happens to be the lower Eagleford. But this workflow, I think, can be applied not just to the Eagleford, but to any unconventional formation or in any unconventional play. And I think ideally could potentially be applied to any play, not just unconventional plays. Once we started to understand what our sweet spot facies were, what we wanted to then do was evaluate the proposed well paths that were given to our client to help them make a more informed decision of which of those well paths would be best, optimal in terms of original oil in place to land and stay within that sweet spot, ultimately hoping to maximize productivity, not just initially, but along the life cycle of the well. So with that in mind, let's take a look at the workflow for the offset well. Now, we were fairly methodical in how we approached this. We wanted to start off with an optimized petrophysical analysis of the well. This would give us an idea of our mineral volumes and the distribution of those minerals. The fluid volumes, specifically what we're focused on here is original oil in place, because we're in the oil window for the lower Eagleford. And then we wanted to then take that information and build a mineral facies using machine learning. From there, what we wanted to do was understand the geomechanical properties along our wellbore. So we're going to look at our elastic rock properties, and then we're going to take that information and build a mechanical facies model using machine learning. Now, these two, the mineral facies and the mechanical facies, are a great start, but what we really wanted to do is to marry that information together to help us find and identify our sweet spot facies. So we took those two facies models and combined them to create a synthetic facies model. And we evaluate that synthetic facies model to find that true sweet spot facies relative to original oil in place. Now, this is all well and good, but that was only the first part of the workflow. We then needed to apply that information, what we knew in the offset well, to our two proposed well paths, the horizontal wells. So we wanted to evaluate the proposed well plans relative to the 3D surfaces provided to us by the geologist, but we also wanted to evaluate the well paths based on the log properties that we modeled from our offset well. So this includes the wireline logs like gamma ray density, sonic, and so on. but also our mineral and fluid volumes, calculated through the optimized petrophysical approach, and our electrofacies models. All of those are going to be forward modeled along our well path, and we're going to evaluate the two well paths and see which one gets us into that sweet spot and stays in the sweet spot longer. The idea is the sooner you get into your sweet spot and the longer you stay in it, you can easily maximize your productivity right off the bat, but not just right off the bat, along the lifespan of the well, as I mentioned earlier. Now, I mentioned that I prefer to show instead of tell, so what we're going to do is we're actually going to get out of the PowerPoint presentation. We'll come back to it to wrap up. What I want to do now is actually get into the workflow. So we're here in the Geolog well window. Okay, I'm working specifically in Geolog 20, and we'll start off by taking a look at our well paths here. So we've got offset plan, our geosteer offset well here, where we come in and we turn a bit shallow. We stay pretty much in the middle of our lower Eagleford here as we come along the well. We're basically staying right in the middle part of the lower Eagleford, which is our zone of interest, don't forget. Then we've got this other well path, which is the geosteer 0 well path. And you'll see what we do here is we come in deeper, we turn deeper, and we stay basically right along the base of the lower Eagleford through the length of the well. So those are the two well paths that we're ultimately going to be evaluating. But before we can evaluate our properties along these well paths, we actually need to generate those properties. So that brings us to our offset well. So here in Geolog 20, we've got our main document viewer here, and we've got a list of our different views here. But one of the things that I've done is I've created a custom menu here. And this is one of the things I love about customizing within Geolog. I can build my own custom menus, as you can see here. And what this allows me to do for the purposes of presentations like this is stay on track, make sure I remember the steps of the workflow that I'm presenting, but I can also use it as a mentoring tool. So if I've got junior petrophysicists that I'm working with, I can build a menu like this and step them through the workflow. And it gets them to, think about, okay, we're calculating shale volume right now. Now we're going to calculate porosity, saturation, permeability. We're going to go through and do rock quality work, things like that. But it helps them sort of key into the workflow and understand the steps of the workflow. For me, it helps keep me on task. We do a really good job of laying out our different modules in a workflow order. But here I'm running a few different workflows, so I want to pull them into my own custom menu. And as you can see, I can customize my display however I like. I can peel things off and move them in whatever fashion I want. Okay, so that's another thing I really love, how I can customize this interface to suit my needs. But let's take a look at the well at hand here. So we're going to bring up an overview layout that I have, and I'm going to focus just on the three zones here. So we've got the Eagleford, the lower Eagleford, and the Buda here. And you'll notice that a deterministic analysis was already done on these wells. We've got total porosity and saturation, as well as effective porosity and saturation here. I'm not so worried about that right now. What I'm focused on are, what I'm seeing with regards to my logs. You'll see here I've got a relatively clean gamma response in the Buda, which we expect. Then we get a jump as we come into the lower Eagleford. And it sort of comes back down, but then we get a slightly higher area here. And we can see that translated into our shale volume here. Now, there's been a bit of debate about where we should draw that lower Eagleford boundary. And we've gone here at about the 20, deeper than 2060 to 2060 meters. But some people could argue that you could come up to 2050. And what you're going to see as we go through this workflow, there are very compelling reasons why we have the boundary where we've got it. So we're going to take a look at that as we step through the workflow. Now, this just gives us an overview of the data that we're working with in our offset well. What we want to do is actually generate a mineral volume and fluid volumes using an optimized petrophysical approach. In Geolog, we call that multi-min. You might know the technique as probabilistic petrophysics or mineral inversion. I refer to it as optimized petrophysics because that's really what's happening. It's not really probabilistic. It's more optimized because what we're trying to do is optimize and reduce our error as we go through the different iterations of the technique. And so that technique I'll touch on a little bit, but I'm not going to go into as much detail as we probably could. I could probably do an entire session on optimized petrophysics, honestly. But the idea behind optimized petrophysics is you know what your tools are, you know what your tool responses are, the tool equations, the tool physics, and what you're trying to do is calculate your mineral and fluid volumes. The idea here is that as you vary your mineral content and your fluid content, your log responses are going to change accordingly. Because the log responses is really responding to the bulk rock, which is all of the different minerals and all of the different fluids. So as you change the volume of one or more, that's going to impact the log response, okay? Now, the way optimized petrophysics works is ultimately it's basically matrix math in the background. We're trying to reduce our uncertainty. We're trying to reduce our error. But you need to start off with your knowns. These are your equations, your wireline logs, or your core equations, or your XRD infrared data, or your petrography, or user-defined logs. In this instance, we're going to keep it simple. We're just going to use density, neutron, sonic, gamma ray, in this instance, total gamma ray with spectral thorium and potassium, plus shear velocity as well as our conductivities. Now, for volumes, we're going to start off keeping it simple. Quartz, pyrite, kerogen, heavy mineral, calcite, plus illite. We're in the oil windows. We've got oil, and we've got bound and free water. Okay, so what we can do is I can go ahead and run this particular model here. All right, and we can take a look at the results. And I'll just hide my empty tracks here. So we're just looking at where we've got data. And right off the bat, I know somebody is going to look at the Buddha and say, oh, there's too much quartz there. You're right, there is. But I also want to draw your attention to the tracks over here on the right, where we've got our wireline logs in black and our predicted logs in red. So that's one of the things that you get from the optimized petrophysical approach is you get these predicted logs. Because you know the tool physics, you can basically come through and calculate predicted values for your logs, and it acts as a really good way to QC your data. So mathematically, if we zoom in here, what you'll see is that all of our logs, with the exception of a couple of places on our conductivities, give a really good match, including in this lower area in the Buddha. So mathematically, the model is fantastic. But geologically speaking, the model's not so good. It's great from the upper Eagleford through the lower Eagleford, but not so good when we get into the Buddha. It's really not appropriate to use a model that's got quartz in it for the lower Buddha because we don't have quartz in the system, or if we do, it's not very much. So what we're going to do is we're going to come back here, and I'm going to switch to a simple model. Everything else is the same. The only thing that's different is that I've removed quartz as an option. So it's just got so I've removed quartz as an option. So it's a calcite-specific model. So we'll run this again. And when we come back, now we see something that is a bit more appropriate. We see a calcite-rich Buddha formation. We see an increase in our illite as we come into the lower Eagleford and quartz. We also see this dark gray. This is our kerogen, and you'll see that kerogen drops off at this boundary between the upper Eagleford and the lower Eagleford. And it's that right there why we have the boundary where we've got it. We're going to come back to this boundary here when we get into the geomechanics because there are some interesting things that we're going to see here in a second. But the other thing I want to draw your attention to is the fluid volumes that we've calculated. So we've got our unbound water. We've got our U oil. This is our original oil in place. Okay, so U oil is basically the equivalent to original oil in place, and we're gonna basically be using this log as we carry on to evaluate what we see here in the offset well, and then what we see in our horizontal well paths. Okay, now that we've taken a look at the mineral model here, and also I want to just very quickly sort of draw your attention to, again, to the QC logs here. We still get a very good match in the Buddha here. even though we took quartz out, we still get very accurate reconstructs here. So this model is mathematically more accurate, but it's also, more importantly, geologically more accurate. So the optimized petrophysical approach will give you non-unique solutions that mathematically may work. You have to use your skill as a geologist or a petrophysicist to make sure the model is applicable to the data that you're applying it to. And that's what we've done here, is we've updated this so that we've got something that's appropriate for the Buddha, plus something that's appropriate for the lower Eagleford and the upper Eagleford. Now, we're going to switch gears. Now, I know in the workflow overview, we actually built the mineral facies model. We're going to do the machine learning collectively here in a second. We're going to do the geomechanics first. So we're going to start off by calculating our isotropic elastic rock properties here. Now, we do have tools to calculate anisotropic elastic rock properties. That's a little bit out of scope for this particular talk. But we do have the capability to do it within our geomechanics workflow within Geolog here. What I'm going to do here is go through and calculate our different moduli plus Poisson's ratio. And we've got the option here to convert from dynamic to static using an empirical relationship for Young's modulus. And you'll notice we've got a bunch of published algorithms here, plus some generic equations that you can use if the published ones are not good enough. So you can really customize this as you need. So we'll go ahead and run this guy. And then the next thing I'm going to do is calculate unconfined compressive strength. Again, we offer a lot of different published algorithms based off of lithology here, plus a number of generic ones as well. You can also assign an existing log if you so choose, but I'm going to work with limestone Onia. We're going to calculate unconfined compressive strength. And then we're going to take a look at the results here. Okay, so if I scroll down, what I want to draw your attention to is starting off with the moduli here. On the left-hand side, we've got all of our input logs from caliper through sonic. Then we've got our different moduli, bulk, shear, P-wave, and Young's modulus, Poisson's ratio, unconfined compressive strength. And we've got our intervals listed here. What I want you to notice is that as we go from the Buddha into the lower Eagleford, each of our dynamic moduli and our static moduli, we see a pretty significant drop-off as we go from the Buddha into the lower Eagleford. This is not necessarily unexpected. There's a very significant geomechanical difference between the Eagleford and the Buddha, and that's what we're seeing here. This also plays out in our unconfined compressive strength here. You can see we've got very high values, and then we come in and we get very low values. Now, you'll notice what I want to draw your attention to is we've got the lower Eagleford here at just right below, a little bit deeper than 2060, but you'll notice that our unconfined compressive strength values are about the same up to just a little bit deeper than 2050. And so from a mechanical perspective, the lower part of the upper Eagleford and the lower Eagleford are actually incredibly similar. Okay. Now we can take this a step further. We can actually look at these results within a ternary diagram here. So I've populated this ternary diagram with my different volumes here. And what you can see, I'm coloring by Young's modulus here, okay? And what I want to draw your attention to is the warmer values in this instance mean higher Young's modulus values, okay? And what you'll see is I've got higher Young's modulus values as I increase my calcite content, but not just that, I see higher Young's modulus values as I also increase my quartz content from clay. Okay, so you can see as we go from wet clay to quartz, we're going from blues into greens. As we go from quartz to calcite, we're going from yellows, greens, yellows into oranges and reds. But also notice as we go from calcite to wet clay, there's actually a quicker transition in here going, this way. We're seeing a significant drop off as we go from calcite and we drop off our calcite content here. So that's actually pretty fascinating. Okay, so at this point, we have done our optimized petrophysical analysis. We've done our geomechanical analysis. What we're going to do next is actually take a look at the machine learning approach. And one of the other things I can do here is I can actually say show splits, and I can see where the bulk of my data is, right? So you can see I've got my Buddha here. That's where the bulk of the calcite information is. We can see the lower Eagleford right here. You can see these are the values that are sort of in the middle of our zone here, where we're seeing more mixed muds. Our delicious, we've got sort of more mixed muds right in here. And then obviously right along here where we've got zero calcite, zero volume of calcite. And the upper Eagleford is sitting really more in this quartz-dominated field here. So we can look at those on a per interval basis very easily like that. But now what I want to do is actually switch gears and talk a little bit about machine learning. And this is a topic that I get really passionate about. And in Geolog, we have a tool called facies. And facies offers a few different techniques for cluster analysis, which is what we're focusing on right now, as well as log prediction. We're going to focus on cluster analysis for the purposes of this talk, and we're going to start off by building our mineral model. And what I want to draw your attention to is that we're using our different volumes to build our model. So we're using all of the different mineral volumes and fluid volumes, our U oil, which is the original oil in place, and our water. We can take a look at the distribution of those logs here on our training data. This is what's been used to build our model. We can look at the cross-plot relationship for all of these guys here as we need to. And these are all dynamic, so if I wanted to bring one up, for instance, maybe I wanted to look at quartz versus wet clay, I can double-click on it and it'll bring it up, and it shows me, you know, the distribution in this instance of the facies. We'll talk about that a little bit more here in a second. Now, one of the things that I get really passionate about, as a scientist, I really want the data to speak for itself. And I want to be very careful about my biases and letting my biases influence my, my decisions with my data. And I have to admit, I do have biases about my approach to machine learning. For me, I really want the data to speak for itself. You'll notice that our different clustering techniques that we have available within facies are MRGC, which stands for multi-resolution graph-based clustering. We've got dynamic clustering and ascendant hierarchical clustering plus self-organizing map. Now, with dynamic clustering, ascendant hierarchical clustering, and self-organizing map, these three techniques basically require you to specify how many facies you've got present, how many facies you want the model to find. Whereas with multi-resolution graph-based clustering, or MRGC, you specify the minimum number of facies you hope to find and the maximum number of facies you hope to find. And what MRGC is going to do is it's going to give you multiple models getting as close to that minimum and as close to that maximum as it can. And for me, that's brilliant because it means I'm taking myself out of the equation and I'm really letting the data speak for itself. I'm probably going to have some preconceived idea of how many facies are there, but let's see if the data really bears that out. So for me, I tend to focus on MRGC. So what is MRGC? Well, it is a K&N approach to cluster analysis, but it's coupled with course-defined self-organizing map. So if I bring up my parameters here, with MRGC, as I said, you specify the minimum number of facies you want it to find, the maximum, in this case, 1 and 35 respectively, and how many models you want it to split those different facies over. And we have this guy here, this initial neurons course-defined self-organizing map. This, to me, is what takes the K&N approach to cluster analysis to the next level. This course-defined self-organizing map is what goes through and helps us order our different facies and orders them in a way that makes geological sense. So we get these natural clusters of data that are organized in a way that we might see in the natural world, geologically speaking. And for me, that's very compelling. I think a lot of people get really tied up and use dynamic clustering, ascendant hierarchical clustering, and self-organizing map. Now we're getting people working in deep neural nets and things like that. And I think all of those different techniques have their merits. But K&N with course-defined self-organizing map is incredibly powerful, and I've seen the results multiple times with multiple clients. So for me, as I said, I get very passionate about this. So what we did, as you can see from the parameters, is we said, see if you can find as few as one facies, as many as 35, over 35 models. The smallest model it could give us was a 3-cluster model, and we can take a look at the distribution of our facies here. And the most it could give us was 35 facies. So it did hit our maximum, but it did it in just 12 models. Now, I could spend a whole other talk going through the mechanics of facies, and it's something that is near and dear to my heart, and I would happily do it if people are interested. But we're going to focus now on the results that we got for this particular study. So we have this 15 cluster analysis that we've got here. And in this one, what we noticed is we've got facies 1 and facies 2, and they're very similar. These, what you see here beneath the volume of wet clay, quartz, and so on, these are the individual histograms of the different volumes for each facies, right? So it allows us to really look at how we're defining these different clusters for this facies model. And what we saw was facies 1 and 2, numbers 1 and 2, are so close that we decided to merge them and come up with this 14 cluster model here. And what you can see here, so now we've got this facies 1, which has 70 points in it. And if I scroll over, what I want to draw your attention to are two things. The cooler colors represent those facies that have higher calcite volume. We see as we come through here, we're seeing an increase in our quartz volume. And then these lower facies, where we've got these warmer colors, what we're seeing is an increase in not just kerogen, but our original oil as well. And we can see, and corresponding with that increase in our original oil, we see a decrease in that water. Okay, so this is what I mean by natural groupings of data. We can see that in the histograms here. It plays out when we actually take this and propagate it to our well. Now we'll take a look at the results here in a bit. What I want to do next, though, is actually go through and build the mechanical facies model. Okay. Now here, what I'm using for my inputs are my different moduli, my Young's modulus, bulk modulus, compressional modulus, and shear modulus. Okay. Now, I've had people ask me, why are you using the moduli? Is that not sort of double dipping in a way? And my response to that is, what I really want to look at in this instance is I'm looking at the stiffness of my material. I could bring Poisson's ratio in, or I could bring brittleness in, but for understanding the stiffness of my material, looking at the moduli is a good starting point. And so that's really where I wanted to start, and I found that the results I got were actually really compelling. So I kept with it. So here, if we look at the models here, you'll notice we have a 14 cluster model. Because we had a 14 cluster model or 14 facies model for the mineral facies, we decided to stick with that. So we had the same number of facies here. And if we look at the facies breakout by histogram, okay, what you're going to see is that, our higher values for our different moduli are going to have cooler colors, and our lower values for our different moduli are going to have warmer colors. So the cooler colors are going to have higher Young's modulus, stiffer potentially. The warmer colors are going to be less stiff. So we're going to take this and we're going to go ahead and propagate that 14 facies model to our well. And we're going to look at the results of that mineral model and that mechanical facies model here. Okay. So here's our layout. And we can see our inputs here. So we've got our mineral volumes here. We've got our different moduli here. And you can see the results for the mineral facies. If I pull this down, is the left facies track here. And if you recall, I said the blue facies corresponded to higher calcite. That's what we see here in the Buddha. As we come into the lower Eagleford, we're seeing, that's where we're seeing an increase in our kerogen content and our original oil. So we're seeing warmer colors through here. Remember that kerogen and the original oils dropped off as we got to this boundary between the lower Eagleford and the upper Eagleford. And that's what we're seeing here. From a mechanical perspective, we've got these facies here, this blue facies, which corresponds to those higher moduli values. Remember, we're coming into the lower Eagleford. We're expecting to see lower moduli values, and overall, that's what we see. What's interesting, though, is we see these higher values as we come into the lower part of the upper Eagleford. Remember, when we went through the mechanical properties, we saw that there was a similarity, mechanically speaking, between the lower part of the upper Eagleford and the lower Eagleford, and we see that with these, that bears out with these facies too. So this is all well and fine. We've got these two individual facies, but now what we want to do is actually see if we can marry these guys together, build a synthetic facies, and evaluate that synthetic facies to determine which of the individual facies is our sweet spot facies with regards to original oil in place. So what we did here was simply take our geomechanical facies model and our mineral facies model, and we used that to come up with a cluster model. We did the same thing where we had a minimum of 1. I think we increased our maximum to something a little bit higher, but here the lowest it could go was 26 facies. So we're going to actually propagate that guy out, and now we're going to look at our final results here. So that synthetic facies is this track here on the right. So the mineral facies plus the mechanical facies gives us the synthetic facies. And I want to draw your attention to a couple of things. So we still have, this blue facies down here in the Buddha. There's a bit of red here. I'm not concerned with that because the Buddha is not on my radar. What is on my radar is this lower Eagleford. And what I'm seeing in here is some yellows, almost chartreuse kind of colors in here that's fluctuating with reds and oranges and greens. And then we hit this boundary, right? So this boundary here, we see a very big change going from the lower Eagleford into the upper Eagleford. That's something that doesn't bear out in the mechanical facies, but when we combine the mechanical facies with that synthetic facies, we see that translate into, oh, this is really our boundary here, which is actually quite cool. Okay, so this is all well and fine, but now how are we going to evaluate these different facies to determine the original oil in place? Well, the easiest way to do that is through a histogram. So I'm going to pull up a histogram for my offset well, and I'm going to focus on, you'll see here I've got my 3 different zones selected. For all 3 zones, it's giving me a mean value of about 4% original oil in place. And what I'm going to do is I'm going to just zoom in here so you can see a little bit better what's going on. So I'm filtering where I've got original oil in place greater than 0.5% basically. Basically, I'm saying let's filter out let's make sure we're looking at where we have oil, okay? Where we have values for original oil in place. Now, we really want to key in on our lower Eagleford because that's our zone of interest. So when we do that, our mean value jumps to about 6.7%. And when we do that, and we're looking at this box plot, right, we're broken out by facies. When we look at these box plots of each of these facies, well, this facies 19 really stands out. You can see our minimum is about 3% with our maximum hitting about 19%. And the mean value is this line in the middle of the box. That's hitting at about 10%. So from this, it becomes pretty clear that facies 19, with regards to, this is our, based off of original oil in place, is our key sweet spot facies. So you can see we're plotting original oil in place as our log, and we're using the color expression for our synthetic facies to basically block this out by block, okay? So to me, this is actually really informative. It tells me, this facies 19 is what I really want to look at. Okay, so that's great. So how do we do that against these other 2 wells? Well, I'm going to split my view here, and what I'm going to do over in this other view is I'm going to bring up the initial well plan, and I'm going to select my geosteer_plan well. And when I don't have intervals there, so I need to select well all. And when I do that, after I've forward modeled all of this information along my wells using our offset model tool, you'll see that I've got a 0.72 or 7.2% mean value for original oil in place. But again, it's this facies 19 that really stands out. The mean value is sitting, maybe at 10.5, with the maximum sort of being right around the same. We're going down to about maybe 7% here, but it sort of stands out against these other guys. The mean is about the same of our offset wells. That's not bad, but we have another well path to evaluate. So what I'm going to do, just do a zoom overview here, is I'm going to split my screen again, and I bring up the other well path here. And this one, I'm going to select the plan 0 well, okay? And I know this is zoomed out a bit, so what I'm going to do is actually do this here. I'm going to minimize the offset well and put these guys side by side for now. So when I look at this plan well, this plan 0 well, well, this actually becomes incredibly compelling because what we see is that our mean value for original oil in place jumps to almost 17%. We're looking at 16.8% here. And that facies 19, well, it's going from just below 10% to just above 20%, with the mean value sitting maybe 18%. So again, it bears out again that this facies 19 is our sweet spot facies. And it also suggests that this well path is probably getting into that sweet spot facies sooner and staying in it longer than the plan 0 well. So if we sort of look at these guys side by side, that's pretty significant and pretty compelling. What we want to do, though, is actually take a look at the well paths themselves. So this top well, remember, is the plan well, the first well. We come in, we turn a bit shallow, and we're staying really right along the midpoint of our lower Eagleford Formation here, okay? We're staying pretty much in the midline here. Whereas this other guy, we're coming in deeper, and we're actually sitting along the lower part of the lower Eagleford over the length of the well. And on the bottom track here, you can see our facies. We've got our facies displayed here, okay? And what you'll see with this first well, the shallower well, is that, we initially hit that sweet spot facies, but we come out of it, and then we hit it. We don't hit it till about, much deeper here. And then we're kind of bouncing around. We keep coming out of it. Whereas this other well path, what we see is we come in and we hit it. We hit that sweet spot facies. We hit it a couple times, but then we land in it. We land in it again, and we actually are staying in it along the length of the well. And because we're getting into that sweet spot facies sooner and staying in it longer, ideally that should translate into maximizing our productivity up front, but not just up front, also over the lifespan of the well. So, what I hope I've showed you over the course of this workflow and some of the tools that we have within Geolog is how an integrated approach to the petrophysical analysis, basically taking, by integrating our petrophysical interpretation, our geomechanical information, as well as using machine learning to help analyze all of this data to identify our sweet spots within our zone of interest, we can then also take that information, propagate it to our proposed well plans to help us determine optimal well placement. In this instance, we determined optimal well placement in terms of original oil in place. But you're not limited to that. And that's the beauty of this workflow. This workflow provides you a concept from which you can work. So you can work with original oil in place, but that doesn't have to be the what you work towards. If you want to maximize in terms of kerogen content, or you want to maximize in terms of brittle content, or how brittle a formation is, or frackability, you can do that as well. The key is that we've got the tools to do it, and we leverage it. And in this instance, I think we have a pretty compelling argument to make that, choosing that plan 0 well is probably the best well to move forward. Unfortunately, the company that we did some of this work for, I believe they divested the well before they divested the data. I don't know that they actually moved. I don't know if they move forward with drilling and making a decision in drilling. So for me, it's just an untold. It's that last little chapter. I don't know. It's a question mark. But the data that we present, the data that we show is fairly compelling. And with that, I'm going to bring this portion of the presentation to a close, and we're going to open things up for questions here momentarily. So I am going to stop the recording. Thank you so much for joining us.